I think I did get a quiz from you if I remember right, yes.
Sounds good.
Okay, so Unit 5 is basic geometry and some of the features that go with it. But there's some background information we need in order to do some of the calculations we need to do with geometry. And one of those concepts is the idea of a ratio. A ratio is nothing more than a comparison between two numbers. You could say two or more numbers because it is possible to have, three-way and four-way ratios. For example, let's do a ratio of students in applied math to students in technical math. So right now I still have 4 students enrolled in applied math, and I have 12 students in tech math. So there are several ways we can write that. We can write it as a fraction, 4 over 12 like that. I can write it with a colon in it like this, 4 to 12, or I can even write it out with the word 4 to 12. Now there are some implications here that we'll talk about in a little bit. But let's go back to these other two forms. I like the fraction form because there are a lot of things we can do in the fraction form that we're used to doing with fractions that are similar to what we did with the fractions. One is to reduce it. We know both 4 and 12 can be divided by 4. So we do that. 4 divided by 4 is 1, and 12 divided by 4 is 3. So we get a 1 to 3 ratio. Now we can still do the same thing in this form. It's just we're not used to it. So it looks a little different, but we would just, both 4 and 12 can divide by 4. 4 divided by 4 is 1. 12 divided by 4 is 3, reducing that ratio to a 1 to 3 ratio. And of course, we can do the same here. Divide both of those by 4 to give it a 1 to 3 ratio. Now, I mentioned the way this is worded, 1 to 3, implies some things. It implies that these two things are separate. Now, that might be implied. You might think, well, that's assumed, but not necessarily. I might say that of the 16 students, of my 16 technical diploma students, 4 are in applied math. Well, that would not necessarily be expressed as a 4 to 16. That would be expressed as 4 out of 16. So when the wording is like that, out of, that implies that this is part of that. So that 16 here actually includes these 4 plus some others that don't meet the characteristic we're looking at. So here we are comparing 2 separate pieces to each other. Here we are comparing a piece to the whole thing. Almost like a percent. In fact, a percent is a type of ratio. Let's do another example. The tables in the classroom. I realize you're not in the classroom today, but let's do a length to width ratio. Those tables are 18 inches wide and 72 inches long. Now, first thing we'll note is the inches divide out. Actually, I said length to width, so let's I gotta adjust it. Let's put my width first. It should be 72 inches to 18 inches, length to width. So the inches do still cancel out. Both 17 and 18 can be divided by similar numbers. Same numbers. They can be divided by 2, 3, 6. In fact, they can go all the way up to 18. Both of them can be divided by 18. 72 divided by 18 is 4, and 18 divided by 18 is 1. Now, here's where our ratios differ from fractions a little bit. If this were just a pure fraction, we would just write that as a 4. But we can't do that with a ratio, because a ratio is a comparison between the two numbers. We have to leave it as 4 to 1. Have to keep that comparison in there. The other thing we might notice here is there's no units there. The inches canceled out. Because when we're comparing length to width on our table, it doesn't matter what units we're using. For every, if we said there's inches, it'd be for every 1 inch of width, there's 4 inches of length. Or if it was centimeters, for every 1 centimeter of width, there's 4 centimeters of length. Or feet, for every 1 foot of width, there's 4 feet of length. The units don't matter because it's the ratio between the sizes, not the actual units themselves. We'll notice in both of the examples of ratios that we have done so far, we have had the same thing. This was comparing students to students. This was comparing inches to inches. And that is a requirement for a ratio, is it must compare two numbers or numbers with the same unit, the same label. Or, like what we said earlier in the semester, with the same name. So if I have something like 2 feet compared to 18 inches, that's not a ratio. Now, fortunately, I can change the name of that 2 feet, and I can change it to 24 inches. And now it's 24 inches to 18 inches, so it is a ratio. I'm comparing things with the same units or same name. The inches will cancel out then. A ratio will always be unitless. It'll have no units because we're comparing two things with the same units, so the units will cancel out. Both 24 and 18 can be divided by 6, giving me a 4 to 3 ratio. Now again, if this was just a fraction, we would want to reduce that to a mixed number. But since it's a ratio, we never want to do that. We will always leave it like that. Even though it looks like an improper fraction, it's not. It's comparing 4 to 3. So what happens if we compare two numbers that do not have the same units and we can't adjust them like we did here? For example, let's say we go on a road trip and we travel 365 miles in 7 hours. There's no way I can change hours into miles or miles into hours here. So this is not a ratio. This is what is referred to as a rate. So that's the first big difference between a ratio and a rate, is a ratio compares two things with the same units. A rate compares two things with different units. The second big difference is that a rate is almost always expressed as something called a unit rate. What a unit rate means is the second number is reduced to a 1. So instead of per 7 hours, this is per 1 hour. And the way we accomplish that is we just divide both numbers by that numerical value. Both of them will divide by 7. So 365 miles divided by 7 is 52.142857143 miles. And of course, 7 hours divided by 7 is just 1 hour. So now it's a unit rate. It's compared to 1 unit in that second number. And because of that, we often, or almost always actually, change how we write that. We simplify how we write it. So first of all, I'm going to round this top number to 52.1. And instead of doing miles over 1 hour, we abbreviate it so that the units, the fraction, is hidden in the units, miles per hour, like that. In fact, sometimes we abbreviate it even further. We might call it 52.1 mph. We have to be aware, however, that whenever we see something like that, there is more implied. For example, let's say on that trip, we get 26 mpg. Well, we know that mpg stands for miles per gallon. So when we see that, we need to be thinking that what that means is 26 miles over 1 gallon. Because this is the form we need it in if we're going to do any calculations with it later. So common rates, we see them all over. We just saw two of them there, miles per hour, miles per gallon. We might have something that is 240 pounds spread out over 4 square feet. Both of those can be reduced by 4. Make it a unit rate. So the 4 square feet divided by 4 is 1 square foot. 240 pounds divided by 4 is 60 pounds. So that's going to be expressed as 60 pounds per square foot. Another common ratio you might run into is you might make $480 in 30 hours. Well, to express that as a unit rate, we will divide by that second number, the 30. $480 divided by 30 is $16. 30 hours divided by 30 is 1 hour. So that is $16 per hour. So these rates are all around us. Ratios are also all around us, maybe even slightly more common. Percents, we mentioned. We covered percents earlier in the semester. We might also run into with our ratios, we might run into something like this. We're going to have to use our imagination because I'm going to draw pictures. And anytime I draw pictures, we have to use a lot of imagination. Good reason why I am a math teacher and not an art teacher. If you haven't figured it out yet, these are gears. We're going to talk about a gear ratio. I know they look like two suns trying to hug each other or something like that. So anyway, a gear ratio goes off the size of the gears. So it's the size of the driven gear compared to the size of the driving gear. Well, first of all, what does it mean to be driven and driving? Well, when two gears mesh together, one of them is the power supply. If I separate the two gears, one of them will keep turning. That is the driving gear. The one that stops turning is the driven gear. It was only turning because it was being driven by the other gear. To know that here, I would have to have more information. So I'm going to do this. I'm going to draw in, pretend that looks like a shaft coming out of that gear. And pretend even further that looks like a little electric motor. So now that larger gear is the driving gear. It's connected to power. If I separate the gears, the larger gear will keep turning, the smaller one will stop. Now, how do we measure size? Well, for two gears to mesh together, the teeth have to be exactly the same distance apart. If they're off by even a couple thousandths of an inch at high speeds, they will bind up and break something. So we can very, very precisely compare the size of the gears by the number of the teeth. So this is the number of the teeth in the driven gear. The number of the teeth in the driving gear. So if I count on this big gear, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 teeth there. On the smaller gear, I got 1, 2, 3, 4, 5, 6, 7, 8. There's 8 teeth there. So 8 is the driven gear, so that's going to go first. This is an 8 to 12 gear ratio. And of course, that can be reduced. Both 8 and 12 can be divided by 4. That gives us a 2 to 3 gear ratio. That 2 to 3 ratio describes a lot of things. It describes the number of teeth between the gear. If one of the gears breaks and we replace it, we have to replace it with a gear of a different size, then we have to replace the other gear with the appropriate gear to maintain that same ratio of teeth. It also is the ratio of speeds between the gears and the ratio of the torque transfers between the gears. So very similar to that, is a pulley ratio. Now, pulleys have no teeth to count, but we're still comparing the size of the driven to the size of the driving. So let me put something that resembles a motor in here. So that smaller pulley is the driving pulley here. And let's say that is 4 inches, and this larger one is 10 inches. So our pulley ratio here, the driven pulley, if I cut the belt, the one that stops is the big pulley. That is the driven pulley. So that's the 10-inch pulley. Compared to the driving pulley, if I cut the belt, the 4-inch one will keep turning. So it is driving. Inches cancel out. Both of those can be divided by 2, giving me a 5-to-2 pulley ratio. Again, that's the ratio not only of the size of the pulleys, but of the RPMs of the pulley and of the torques within each pulley. In construction, common ratio is grade. Grade is rise compared to run. So let's say this is 150 feet here, and this is 9 feet of rise. So the grade here would be 9 to 150. Now, typically, grade is represented as a percent. So we have to change that to be out of 100. So we would do our cross multiply and divide. 9 times 100 divided by 150 gives us 6 out of 100, or a 6% grade. Now that doesn't sound like a very steep grade, but for federal highways, actually 6% is getting close to the maximum. I believe 7 or 8% is what they allow. For state highways, I believe they allow 9%. For grades. For county roads, obviously, I know several that are way steeper than that. But so that 9% is only 9 feet of rise for every 100 feet of run. It doesn't sound like much, but it provides a relatively steep roadway. Highway 8 over by St. Croix Falls, it's a pretty steep hill going down to the river. That is actually, I believe, an 8% grade. So it's not that huge. I mean, it doesn't sound huge, but it is pretty steep. There are all sorts of other ratios that come into construction, and I'm not going to be able to go through all of them here, but I do want to talk about a business ratio that's actually important to pretty much everybody at some point in their life, and that is a debt to income ratio. We talked about unit rates where the second number is always 1. We always convert it to 1. There's also unit ratios where the second number is always 1. A debt to income ratio is actually a reverse unit ratio. The first number is always made to be 1. And we want the second number to be at least 3. Let me show you what I mean by a debt to income ratio. So let's say you're working standard 40-hour weeks. We're going to go as 160 hours a month at $25 per hour. So that is bringing in a very, very respectable $4,000 per month. Now let's look at your debts. Let's say you have a car loan for $400 a month. Let's say you got, what's this car? Credit cards of about $200 a month regularly. And let's say you still got a student loan running about $200 per month. Your total debt here is $800 per month. So your debt to income ratio is your monthly debt. Now notice that does not cover food, gas, any of that. Those are not debts. Those are expenses. Debts are payments on loans. So if you had a personal loan, that payment would be a debt. Credit cards are a revolving line of credit, so the payment actually changes every month, but they'll take like your average minimum payment or whatever for the last 12 months. In fact, normally what they'll do, rather than minimum payment, because banks don't like it when you make minimum payments, they will take your balance and they'll do a percentage of your balance is what they will figure in for that credit card payment for the month. So here we've got $800 is our debt for the month, and our income for the month is $4,000. Now it's a reverse unit ratio, which means we actually divide by the top number here. 800 divided by 800 is 1. 4,000 divided by 800 is 5. That's a 1 to 5 debt to income ratio. Well, we said we wanted that second number to be at least 3. So a 1 to 5 debt to income ratio is actually a very good debt to income ratio. It can change in a hurry. Let's say you want to buy a house. And the house you want to buy right now with real estate prices the way they are, not uncommon. There are very few houses out there selling for under $120,000 right now. Average house price is between $210,000 and $220,000. I've seen some really nasty looking houses. And I shouldn't say nasty. I don't want to insult them, but houses that would have been $100,000 to $110,000 a year and a half ago that have actually sold for $215,000 or $220,000 in just the last few months. So a $220,000 house, your house payment on a 30-year loan is going to be somewhere around $1,000. Now that is not your escrow. Your actual payment might be more like $1,300 to $1,350, because that would include your taxes and your insurance. This is just the payment on the loan. So now that would give us a total debt. We add that $1,000 to the $800, that gives us $1,800. And our income is still $4,000. So now if we divide by that 1,800, of course 1,800 divided by 1,800 is 1. 4,000 divided by 1,800 is, what, 2.222? Something like that. Well, 2.222 is less than 3. So the bank's going to look at you and say, no, buying that house is going to throw your debt to income ratio out of whack. Oh, excuse me. We're not going to. Oh, excuse me. Sorry about that.
Bless you.
Thank you. They're going to say, we're not going to loan you that money because it's going to give you too low of a debt to income ratio. We want that to be bigger than 3. Now, you hear a lot of talk about credit score. Credit score doesn't necessarily determine if you get a loan. If you have a really low credit score, like, a 500 or 475, you might not get the loan just because to get that low, you had to have had a lot of missed payments or defaulted on a loan or whatever. And a bank might say, no, they don't want to give you a loan if you're that low. But if you're at least a 600 or 625 or so, they'll still give you the loan if your debt to income ratio is adequate. If you show you've got enough income to afford the debt, they'll still give you the loan. Having the low credit score just means they're going to charge you a higher interest rate. My car, I think I'm paying a 1.99% interest. Had to have a pretty good, decent credit score for that. If I didn't have a good credit score, my bank would have charged me up to 5.9% or 6.2%, somewhere in there, that it would have been if I had a bad credit score. So it makes a pretty decent sized difference on your payment with your having a good credit score, but it doesn't determine if you get a loan. I know people with an excellent credit score that still can't get a loan because it's going to throw their debt to income ratio out of whack. Now you look at the issues back in 2008, 2007, which you guys would have been fairly young back then, but you probably remember the big housing crash, the mass foreclosures, all sorts of people walking away from their houses because the value of their house went down. What happened there in a lot of cases was government bodies that push for low-income loans and stuff like that were pushing banks to lower their standard. Instead of doing at least a 3 for that second number, they were pushing them to go down to a 2 for that second number. and still give out those loans. So what they were doing was they were giving loans to people that they knew were going to struggle to repay them. They could maybe afford the payment right now if everything stayed perfect, but if they had a week where they got 4 hours less at work, or they got sick and missed a day of work, they were going to be short on their bills for the month. And so it was created by the banking system that caused that all to happen. I won't get any more details on that, but that's basically what happened there. Okay, so your homework on ratios in your book, page 282. It is exercise 7.1, problems 1 through 65, the odd. Tomorrow we will continue with proportions, which will be our next step. Now, Graydon, on Wednesdays, you guys still have